Okay, let's learn about the regression. There's basically three types of regression generally. Well, technically a lot, but in terms of the type of regression we're learning about, we have either a linear regression, which is a single IV with a single DV. We have multiple regression, which allows us to look at multiple IVs on that single DV. And then we have hierarchical regression, where we have a set of IVs, and then we want to see how another set of IVs predict above and beyond that first step. So we're going to talk about the second two, because the linear regression is similarly, basically we've covered linear regression throughout this semester. And if you go to the general linear model chapter that is in your reading, you'll see how the linear regression is equivalent to a t-test, ANOVA correlation, and so on. It presents it in a different way. So we're going to talk about multiple and hierarchical regression for this week, because you should have the gist of a linear regression by now. I have some stuff in the textbook about how to understand regression and how, understanding these residuals and stuff. So read through that. Let me know what questions you have. These are all residuals and stuff. And hopefully that helps make sense a little bit. So we're going to go directly to our example for this week, which is also the parenthood data set. This is the same that we did for the correlation. So let's look at our data real quick, because Jamovi doesn't get this right. This is an ID variable, and this is a continuous variable. Okay. So we've set up our data, we've looked at it, we should understand it by now because we've done it for the correlation stuff, we've described our data. Now we need to check assumptions. And you might look at this and be like, whoa, why would we ever do regression if all of these are the assumptions? The reason why we didn't care about it all that much with the other the linear regression type things like the t-tests and ANOVAs is because a lot of these was actually built into the the test itself, because of the nature of the F distribution and T distribution. But because we're doing regression now, we have all these additional assumptions. It's not that bad. You just have to go through all the different steps. So we actually need to run our regression. Basically, we've already checked for variable types. The DV is continuous and the IVs are continuous, but actually the IVs can be anything. We have all continuous variables here, so that's fine. And then all the outcome variable values are independent. So I think we're looking at, what are we looking at? Do we have our hypotheses? I don't think we've determined just yet. I think, what are we doing? We are looking at Dan's grumpiness, whether Dan's quality of sleep, the baby's quality of sleep, and the baby day, may or may not include it, affects Dan's grumpiness. Okay, so we need to run the test to be able to check all these assumptions. So we're going to go to analyses, regression. We're going to go to, weirdly, linear regression. But we can add all this in. So our dependent variable is Dan's grumpiness. And our covariates, I think we're just looking at the quality of sleep here. So put that in. If we had any categorical variables, we'd put them into the factors box. But because these are all continuous, we put them in these boxes. If you were performing a hierarchical regression, you'd go to Model Builder. We'll talk about that in a second. We only have one block, so we'll talk about that in a bit, like what a hierarchical regression would look like. When you have categorical variables, you can specify which is the reference level for the variables. And I talk about that later in the reading. Under assumption checks, we need to check everything. Awesome. We'll come back to that. Model fit, we're going to check most of it. R squared, adjusted R squared. We can talk about all of these. I'll bring them up in the overall F test. I'll just bring it all up. Model coefficients, I think, standardized estimate, right? Otherwise, we just get the unstandardized estimates. That's not as helpful. I don't think we need, I just say are optional that we could ask for the estimated marginal means and get the plots and tables and stuff. But we're going to ignore that. Okay, so we've run it. We need to now interpret all this stuff. So let's go back to our checking assumption stuff. First, we have an assumption that there are no outliers. There shouldn't be any data that are outliers in our data set. We could look at, and I don't have it up, we could look at the univariate outliers, looking at each variable. Is there an outlier in each variable? But we actually also want to check for multivariate outliers. Are there particular cases of participants that are outliers of the data set? And we can't do that by just looking at the data. We need to calculate Cook's distance. So Cook's distance we've got here. And how do we interpret this? I thought there was a way. Oh yeah, Cook's distances greater than 1 indicate a multivariate outlier. Ours are a mean of 0.01, median 0. Our max is 0.11. So we're looking here, not even close to 1. So we have no outliers in our data set. Good to go. We've met this assumption of no outliers. Now we want to look at normality, but it's not normality of the dependent variable. We've already checked that. It's good. We actually want the normality of the residuals. Now, somebody asked me, I think a couple weeks ago, about why does the Shapiro-Wilks differ depending on whether you run it in the test versus when you run it on the variable itself? And it's because when you're running it on the test, it's the normally distribution of the residuals in the test, but in the variables, it's the normal distribution of the variables themselves. And so, in fact, it's the residuals we care more about. And so we should be running Shapiro-Wilks better in the test as opposed to in the variables box, like the descriptives box. So let's go ahead and look at our normality test. Our statistic is not statistically significant, and our QQ plot of the residuals looks quite good. So we've met the assumption of normality of the residuals. Next, let's check the assumptions of linearity and homoscedasticity. We've already been familiar with both these. Linearity with that correlation, right? The relationship needs to be linear between the variables. And homoscedasticity, that this we learned in the one of the ANOVAs. I'm blanking on which one right now. Basically that the variance is equal among groups. And in this case, because it's not groups, it's a continuous outcome, or we don't have any group variables really. It's just that the variance is the same throughout, that there's no funneling that seems to be happening. So linearity, we're looking at the data. Does it look like there's some sort of like relationship, like a curvilinear relationship? Nope, it looks pretty kind of like a blob. So there doesn't seem to be any curvilinearity to it. So we do meet the assumption of linearity. Now the variance of the data across the plot seems to be pretty similar no matter what's going on, right? And we're looking above and below the residuals of 0. So looking up and down, there doesn't seem to be any funneling happening. So we do seem to meet the assumption of homoscedasticity. Now, I don't have it here. Scedasticity. I'm seeing if I can find a good image. Oh, here we go. So here is what it would look like if we have heteroscedasticity. Ooh, that's a word. So look at the variance down here is small and then gets bigger and bigger and bigger. This is what I mean by funneling. Funneling down, funneling up. This would suggest that we don't meet the assumption of homoscedasticity, whereas we have something more like this, where it's just kind of flat throughout. And then I think here's some examples as well. So we've got some funneling going on, and they put a fitted line to it. This seems to have a curvilinear relationship. So we'd fail the assumption of linearity here too. This is also funneling, and it's fairly flat. It's not too bad. So those are some examples of failing to meet those assumptions. Let's see if I can find any more through here. Here's some more examples of failing to meet the assumption of linearity. Like this one's very curvilinear, right? And maybe not really like this, really just like this big curvilinear thing going on. So this, we would fail to meet the assumption of linearity. Oh, here's some more of funneling, heteroscedasticity, bow tie pattern, fan shape pattern. Ooh, this is a beautiful curvilinear relationship, right? And it's not bad. It's just we would need to change how we're doing our analyses to meet that assumption. So we won't get into that. Okay. So hopefully that helps you understand how to check for linearity and homoscedasticity. We've met those in our data set. We could go back down here. Notice I'm just looking at the fitted and the residuals. We can also look at the residuals for each of the variables, and they look okay. I'm not 100% certain actually why we get all of these specific ones as well, because I think we're only really supposed to interpret this one. So I need to investigate that. Okay, now the next assumption is that the residuals are independent. Oh, that is an error. So we need to make sure that the residuals are not related to one another. And this is called the Durbin-Watson test for autocorrelation. So let's go to Durbin-Watson's. Durbin-Watson here, p-value is not statistically significant. And ooh, they've changed how it's calculated just slightly. P-value slightly different. Anyways, doesn't matter, not statistically significant. And so our residuals are independent. They're not related to one another because this is not statistically significant. We could also look at whether like the values themselves, values less than 1 or greater than 3 tend to be problematic. But we're getting a p-value as well. This is back from SPSS days when I don't think it gave us a p-value. So yay for Jamovi, right? So this is in between 1 and 3, so we're good. And this is the autocorrelation between the residuals. This is basically 0. Okay, so we've met the assumption of independence of residuals. And lastly, we want to make sure there's no multicollinearity. Whew, okay. So we want to make sure that there's no collinearity among multiple variables, no correlation among multiple variables. There's some reasons why multicollinearity can be a problem. It makes the relationship between the variables, the B's, we'll talk about that in a second, really unstable. It can fluctuate with very minor changes. So this becomes a problem. It also affects the size of our R and therefore our R squared, which we want to be big. We want to be able to explain at the maximum amount of variance in our outcome variable as much as possible. And when two variables are highly correlated, it's hard to tell which variable is more important than the other, because it's gonna, what usually happens is if there is multicollinearity and one variable is slightly more related to the outcome variable, it's gonna completely take over and say, I'm the only important predictor and the other one's not. When really you're like, well, they're both strongly correlated with our outcome, right? So, what's up with that, right? Okay, so to test for multicollinearity, the multiple variables are correlated. We need to check the VIF and tolerance values. They're actually the same thing. VIF is a transformation of tolerance, and you could check that, right? So let's run a calculator. 1.65 divided by, 1 divided by 1.65, there we go, is 0.61. So they're transformations of one another. They're inverses of each other. Okay, so we want VIF, VIF values lower than 10 and tolerance values greater than 0.2, because that's the inverse of each other. We meet both of those assumptions. We can check here again. Meet both of those assumptions. So we have no multicollinearity in this case. So we have met all our assumptions. We can move on. I want to pause here real quick and just say, if you don't meet some of the assumptions, for the purpose of what we're doing in this class, I'm going to have you just be transparent about that and say, didn't meet this or these assumptions. Here's how, but I'm going to proceed anyways, right? I just want you to practice testing them and actually running the statistics. Because sometimes in real life, we don't meet the assumptions, and that's fine. Sometimes there's ways we can go adjust it. So for example, multicollinearity, if you've got some variables that are strongly correlated with one another, then drop one of them or combine them into one variable. For example, I think I have at the bottom what to do. I think I need to add that. I will add that at some point of what to do if you fail to meet some of these assumptions. So I'll talk about that. Maybe ask questions in the chat, but I will revise this video and in the future and put that information in. Okay. We've met our assumptions. We've already performed our tests because we've already done all this. And so now we need to interpret our results. I'm just going to go back here. For the model fit measures, this is giving us the overall model fit of the entire thing. How both, in this case, both of our independent variables relate to our dependent variable. So we have a correlation of 0.9. and the R squared of 0.82. And I want to just pause for a second. Remember when we did the correlation and we looked at the correlation, I think between Dan's quality of sleep and Dan's grumpiness, the R was 0.9 and the R squared was 0.81. We're saying that the baby's quality of sleep is adding very little extra variance explained to our model. And in fact, even though these are strongly correlated, and even though Dan's quality of sleep and Dan's grumpiness and baby's quality of sleep and Dan's grumpiness were all correlated, right? We can even check this again. All three of these. I'll put this in here so you can see it again. All of these are correlated strongly. And even though we don't meet the assumption of multicollinearity, we're having some issues that even though they're all strongly correlated, when we go to our regression, Dan's quality of sleep was more strongly correlated than baby's quality of sleep with Dan's grumpiness. And therefore, it's taking over all of the variance explained, and baby's quality of sleep isn't adding anything to our model. So this is what I mean. Even though technically we didn't fail to meet the assumption of multicollinearity, technically, we're still getting some unstable betas because you would expect both of them to be related to Dan's grumpiness. But in fact, when we combine the two variables and we look at them both simultaneously in the model, only Dan's quality of sleep is significantly related to Dan's grumpiness. Baby's quality of sleep, when in conjunction with Dan's quality of sleep, is not. So going back to the model fit measures, if you had multiple models that are considered nested, we could compare these values across the models to see if there's significant change among them. For the purposes of what we do, this is not critical for us, so we can actually just take all this out. I'm just going to take it out for now because it'll ease our work. And I'm going to take all this out because I've already looked at it just to simplify things. And so we see our correlation matrix again. We also get an overall model test, and you should know how to interpret this by now. It's an F test. It's an ANOVA. We have a huge F, so this is statistically significant, and yep, it is. So our overall model of how Dan's quality of sleep and baby's quality of sleep is significantly related to Dan's grumpiness. We get that through all of this stuff. So that's kind of like the overall test. Now, we want to know like what is significant, right? We know that the overall model is statistically significant. So which of the predictors, which of the independent variables is significantly related to Dan's grumpiness? I've already previewed this, right? That Dan's quality of sleep was significantly related to Dan's grumpiness. Baby's quality of sleep, when examined simultaneously with Dan's quality of sleep, was not significantly related to Dan's grumpiness. And these are the standardized estimates. And in fact, because this is just so not significant, because this is just completely taking over, interestingly enough, this matches our correlation because it's Dan's grumpiness, Dan's sleep is just taking over in the model because Dan's sleep and baby sleep are strongly correlated. Okay. So again, we have our R squared and adjusted R squared. Our adjusted R squared is just adjusted for the number of variables in it, I think is basically it. So you'll know it's about the same as the correlation itself. Baby's sleep is adding nothing in predicted variance explained of Dan's grumpiness over and beyond Dan's sleep. So we would report the adjusted R squared over the R squared typically. We have our overall model test. We've talked about that. The model coefficients, standardized fit coefficients. And we could put all this into a linear equation, right? So that's what the intercept is for. So y equals, the average is 125.97. And then we add in minus, and this is our unstandardized coefficient, 8.95 of Dan's sleep, 0.01 of baby sleep. And so if we plugged in some numbers, we could predict what Dan's grumpiness would be. So if Dan's sleep was a 5 and baby sleep was an 8, we'd expect Dan's grumpiness to be an 81.3. So that's what we can do when we get these types of equations. We can now then predict new variables based on the data that we had. Sorry, not new variables. We could predict what would happen in particular cases given the data that we have. And then we could write this up. Okay. Dan collected data on how many hours of sleep Dan and Dan's baby got, as well as Dan's grumpiness for 100 days. Dan tested how the hours of sleep both Dan and the baby got affected Dan. Oh, it's not quality of sleep, it's hours of sleep. Sorry, I've been interpreting that all wrong. It's close enough. Affected Dan's grumpiness using a multiple regression. The combination of predictors were significantly related to Dan's grumpiness. And this is the overall model fit stuff, that first variable, right? The combination of predictors significantly related to Dan's grumpiness. And I put the F test and the adjusted R squared in there. The number of hours of sleep that Dan got significantly predicted Dan's grumpiness. And then I'm putting my beta, which is my standardized estimate. Beta equals negative 0.90, comma, and then the t-test. That's the t-test right here. Standard error, p-value, all that stuff. However, the number of hours of sleep the baby got did not significantly relate to Dan's grumpiness and all of that as well. And I want to make a note, I did not include anything about assumption checking here. I usually discuss how I check assumptions in an analytic plan in the end of my method section. But you could also write it up here as well, that we met the assumptions of, we could say Durbin-Watson statistic and then write that up and so on. So you could write that in to before you discuss the actual results. You could talk about how you tested the assumptions and what those values were in the spirit of transparency. Okay, now let's do a hierarchical regression. And I want you to do baby's quality of sleep and then Dan's quality of sleep. So let's change this. Actually, we'll just run a new one. I'm going to take this out. Remove. Let's do a new regression. Linear. We want Dan's grumpiness as the DV. These are the IVs, but we're going to model build and we're going to add a new block so that it's baby, then Dan's sleep. Okay. I'm going to ignore checking assumptions right now. They should still meet the assumptions just because they should. But you should always check those again. And in the homework, I have you check them all again. I'm going to add that and add that. What is this? Omnibus test. Oh yeah, we can ignore that. You can note how it gives you an ANOVA test, which is just like what we've been seeing with the ANOVA. So we're just going to ignore that. Okay. So it's going to give us the model specific results separately. Let's just overall look at the models. When we just have, and we can go back to model 1, when we just have baby sleep in the model, it predicts about 31% of the variance in Dan's grumpiness. And it is statistically significant, right? That baby sleep is significantly related to Dan's quality of sleep. And I shouldn't have gotten rid of that correlation. Let's go back here real quick. Oops. And in fact, watch this. Baby sleep and Dan's grumpiness is 0.57. 0.57. And 0.57 squared is going to be 0.32. Ooh, right? So this, again, previewing that the correlation is the exact same thing as a linear regression with one independent variable. We get an overall F test that is statistically significant. And then we're going to add Dan's quality of sleep. So this is model 1. Model 1 was statistically significant. baby's quality of sleep did in fact significantly relate negatively to Dan's grumpiness. As baby got more sleep, Dan's grumpiness went down. Standardized estimate of beta is negative 0.57, which matches the standardized estimate of the correlation down here. Then we want to see, what does Dan's quality of sleep do above and beyond baby's quality of sleep? So we add this, and again, baby's sleep just zip, right? It went down to 0. Before, it was statistically significant, but when we add add Dan's hours of sleep to the model, then baby's hours of sleep went to 0. We already saw that with our multiple regression. But now what we then can add is a model comparisons table. What is the significant difference between model 1 with just baby sleep and model 2 with both baby's and Dan's hours of sleep? We get a change in R squared, just a change here of 0.5, and then the F-test of the difference in the two models. F-test of the difference in the two models. So not only does baby's sleep significantly relate to Dan's grumpiness, but Dan's quality of sleep significantly adds to the prediction of Dan's grumpiness by a change in variance explained of 50%, and that overall model comparison is statistically significant. So this is really helpful when we want to see how a set of predictors, one or more predictors, predict the outcome above and beyond a set of predictors. So you'll practice this in the homework, and then we can talk about how to write that up. So I like to write it up of kind of, okay, overall we already knew what was happening with the data. So now we're interpreting the first model. Then we're interpreting the second model. This is the overall model fit. And then we're talking about the model comparison, the second table right here, that model comparison, and then interpreting the model coefficients in the second model. So I'm starting model and then coefficients, and then model compared to first model, then the second model's coefficients. So that's a general gist. There's other ways you could go about it. You could also just put this into an APA table. So there's multiple ways to do this. And then lastly, what to do if you have categorical predictors. So we don't, I did a little practice run where you could change day into three-ish groups of equal size to see if if this relationship holds between the first, second, or third of days of the study. But what I want to point out is the reference levels drop down. So when this happens, you can specify which you want to be the referent group to be. So you'll explore that in the homework, and let me know what questions you have as those arise. And so you can see how these vary by the three groups. Let me know what questions you have. Good luck with the homework this week. I know this is perhaps the most challenging, but as I preview in the general linear model chapter, all of what we learned so far is technically regression. So we've built up to the thing that you could actually use from here on out and never do a t-test again. That being said, in our fields, we tend not to do that, right? Food science tends to use a lot of ANOVAs, at least from what I see. We tend to do a lot of t-test ANOVAs as well. So we tend not to do just regression for everything, even though some people in the stats field think we should be doing that. So let me know what questions you have. Hope this was helpful.